Hello everyone. Today we are going to utilize the fundamental postulates of electrostatics to derive Coulomb's law. Firstly, let's consider the simplest possible electrostatic problem. We have a unit charge Q which exists at the center of the coordinate system, and we wish to find the electrical field generating by this charge. We will start by drawing a hypothetical sphere. This sphere is centered by the origin of the coordinate systems where Q exists, and we will find the electrical field at the surface of this sphere. And the reason behind drawing this sphere that this charge has no preferred direction. It's going to affect the whole space with the same amount of electrical field intensity. Because of this, the electrical field intensity generating by this charge is going to be radial. And let's start by considering Gauss's law. Gauss's law is telling us that the surface integral for the electrical field intensity is equal to the charge generating this electrical field divided by epsilon, and the epsilon is the permittivity, and we will consider this case to be in free space, so epsilon will be epsilon sub zero, the permittivity of a free space. Firstly, let's start by drawing E and D as vectors with unit vector notation. We said that the electrical field is radial, so it's AR times E sub R times ds, and the surface in this case is the surface of the sphere, and we know that the unit vector of the area is orthogonal on this area. As we said before, this area is a sphere, so the unit vector is AR2. It's orthogonal to the surface of this area times ds equals Q divided by epsilon. Now let's find the value of this derivative, the ds. What does ds equals? ds, which is a small area of the surface of the sphere, equals r squared times cosine theta times d theta d phi, where r is the radius of the sphere and theta is the polar angle, this angle which is ranging between 0 and pi, and phi is the azimuthal angle, which is this angle which is ranging between 0 and 2 pi. And later in another video we are going to prove this equation. Yes, let's substitute this into this equation, and we will have the integration for E a sub r times er dot a sub r times r squared cosine theta d phi, okay, equals Q over epsilon. And as we have two derivative components, we will have double integration for the polar angle theta. It's ranging between 0 to pi, and the azimuthal angle phi is ranging between 0 and 2 pi. Firstly, I will start by taking the integration with respect to theta, and because of this, otherwise it's constant, so a sub r is constant, r squared, and when we take the dot product between this and this, the magnitude is 1, so there's no need to rewrite them again. E sub r times r squared times the integration of cosine theta is minus sine theta. It's ranging between 0 and pi times d phi equals Q over E. And let's not forget the integration from 0 to 2 pi. Okay, minus psi pi plus sine 0, it's 2, so 2 er times r squared times d phi. Let's take now the integration with respect to phi. The integration of d phi, it's phi from 2 pi to 0 equals q over epsilon. So this equals 2 pi. 2 pi times 2 pi, it's 4 pi e sub r times r squared equals q over epsilon. This is e. Anyways, sorry, it's not that clear. Anyways, to find the magnitude of the electrical field, let's transfer all of these terms, and we will have E sub r equals Q divided by 4 pi r squared times epsilon. And let's write the electrical field in terms of unit vector notation. The electrical field vector, we said it's radial, so it's AR times E sub r, which is Q over 4 pi r squared times E epsilon sub 0. And this equation is Coulomb's law. This equation is telling us that in order to find the electrical field generating by electrical charge at any point in the space, we only want to find the magnitude of this charge which is generating the electrical field, and the distance between this charge and the point where we want to find the electrical field intensity. We said before that if we wanted to calculate the electrical field intensity at the point P, which is an arbitrary point in the free space, we can use this equation. The only needed parameters are the magnitude of the charge, which is Q, and the distance between the point, which is P, and the charge Q, and which is R. And the direction of the electrical field is along R, which is the distance between Q and P, and it's outward the charge Q. But this equation, as we said before, it's only valid only when the charge is at the origin. So what if we wanted to calculate the electrical field at the same point P, okay, when the charge is not located at the origin? What should we do? Okay, so let's draw this case. We have this point Q, which is located here. It's not at the origin. Okay, so firstly we have the vector r, which is the radius of this sphere, The magnitude of this vector is the radius of this sphere, and this vector is representing the position of the point P. Okay, so firstly the electrical field is going to be along this vector, okay, between Q and P. This is the direction of the electrical field, and let's say it's A sub P. This vector A sub P is representing the direction of the electrical field that P is going to be affected because of the charge Q. Okay, so and let's say that the vector position of the charge Q is represented by this vector, which is r primed. This vector r primed. Okay, so what is the distance between Q and P? As we see, this vector r is the summation between this vector and this vector. When we add these two vectors, we will end up with r according to tip to tail rule. So this vector is representing r. Let's put this bar to show that they are vectors. Okay, this vector is equal to r minus r primed bar. Okay, and now let's use these new vectors to make an adjustments into this equation. Okay, we said that the electrical field is has the direction along the distance between the charge and P, and this vector is AP. This is the new vector that we have. Okay, this is the new unit vector that we have, and the magnitude of the charge is Q, and these are constant, they still the same, 4 pi epsilon sub 0, and r, which is the distance between q and p, is the distance of this vector, and the distance of this vector is the modulus of it, or the absolute value of it, which is r minus r primed squared. Okay, the modulus of the, as we know, the modulus of the vector, is representing this, or the length of this vector. Anyways, let's make another adjustment on this equation and write it with only r and r primed, using r and r primed vectors. Okay, so let's look at this vector. Okay, r minus r primed. This vector, r minus r primed, has the direction of AP. Look, this r is pointing to this direction, and it is the same direction of this AP. Okay, it has the direction of AP. Also, it has the magnitude of the modulus of r minus r primed, so that AP, which is this unit vector, equals r minus r primed minus the modulus, or the length of vector r minus r primed. Now substitute this for this in this equation, and we will end up with the electrical field is equal to q times r minus r primed divided by 4 pi epsilon times r, the modulus of r minus r primed cubed. Okay, and as we see, this equation is valid for all conditions. This equation is only valid when the charge is located at the origin of the coordinate system. But this equation is valid for all cases. It's a generalized form of Coulomb law. R, this is representing the position vector. The position vector of the point P, or the point that we want to measure the electrical field intensity at, and r primed is representing the position vector of the charge Q. And that's the end. See you later.